Okay, here's my example. So on number 2, it's false.
Oh.
So when I picked this counter example, I was trying to think of, x squared is our classic counter example of something that's not uniformly continuous on the reals. So how can I make that x squared behavior happen in something that's bounded? Well, the obvious thing is to take x squared and stick it into something that's bounded. So that's how you can think of this example. So I wanted to first show that sine of x squared is continuous with the definition, and I'm going to ask laptops to be closed as I'm going through this, other than you're taking notes. Yeah, you want to keep that picture. So I went down this rabbit hole, but I think it's okay. You can use a Bartle theorem that says that if you have two continuous functions, then the composition is continuous. But I only thought of that after. So we're going to go through the dirty work. Because the reason why I want to do all of that is you're going to see that when I show the continuity, that the delta is dependent on epsilon. That doesn't prove that it's not uniformly continuous, because I could have just made a bad choice of deltas that happen to be dependent. Probably when you took these courses, I don't know. I was trying to remember all my trig identities. So let epsilon greater than 0 be given. I need to find a delta epsilon such that let me see if I did this forward. I did it.
The delta could be.
Well, it's just copy.
Oh, this is just.
All right, so here's what I needed to do. The problem with my choice of this awful function was that I need to get the stuff here, like when you did your problems, which basically a lot of you actually messed up on doing the forward proof after the scratch work, but you need to somehow isolate your x minus c. And the problem is my x squared is buried inside a sine. So I need to somehow get the x out of the sine to do the scratch work to get the x minus c to be less than delta. And so I went back and thought, how do I get the x out of there? And well, you can get the x out of there pretty easily if you know that the function's differentiable, but we're not in that chapter yet. So the first few attempts I went, oh, okay, can't do that. But I'm going to tell you that sine of theta, and I'm using thetas here because I'm going to replace the theta with something, but just to bring you back to the world of unit circles, this is going to be less than theta for theta. And it wasn't good enough for me just to say that's true. I wanted to see why that was true. I know it's true because sine theta, when you expand it as a Taylor series, I get sine theta is equal to theta plus a bunch of garbage. So I can like show using some analysis that if theta is small enough, all these other things will disappear, and I'll get approximately sine theta is equal to theta. Also, you can see from the graph, if I have y equals x, and I graph sine x, it's going to be under the line y equals x, that first quadrant. And so I knew that this was true. Let me the other side there. I got absolute values, so I want to see that. How do I see this? Well, unit circle. Let's suppose I have an angle, theta, and I drop this down here. Because I went back, like, I kept going to some differentiation. You can also use mean value theorem, but mean value theorem requires differentiability of the function, and we're not on that section, and I don't have mean value theorem yet because it's going to be proved ahead of time. In fact, we're proving it on Wednesday. We're doing stuff with that on Wednesday. We don't have that yet. But here's sine of theta is equal to this opposite over hypotenuse. But the hypotenuse is touching the circle. This is the unit circle. So what's the distance on the hypotenuse? What? So I have that. So sine of theta is this length here that gives you this opposite. Let me see if I can read my writing because I didn't use a color. Okay, the next thing I know is that if I look at this distance here, it's 1, and I have this sector. Remember sectors? I'm laughing because I didn't particularly like this kind of math, but the area of that shaded piece, that sector, is equal to the fraction of the circle I've gone all the way through. So that's going to be theta divided by 2 pi because the circumference is 2 pi. So I've just chopped off theta divided by 2 pi. So that's the fraction. Times the area of the unit circle, pi, over 2. And don't make me prove this, but the area of that triangle is going to be smaller than the area of that sector. I was pretty unhappy by the time I got to page 3. I'm like, this is like nasty. For this, but to take your math test for a Jedi, even your math test to be placed in a 103, you had to take a test, fundamental concepts test, and they have all these unit circles. I look at that one, I don't know if I'd have that. Yeah, we're out of time. So I'm going to finish this up next time, Wednesday, to show you why this is continuous. And then you'll see the deltas dependent on epsilon, and you'll hate me for choosing this particular function as my example.